All right, welcome everybody to the Symposium. Thank you for coming to our keynote address. I just wanted, my comments will be brief, but one of the things I wanted to mention to you all today, particularly students, is that high impact practices are active learning practices that promote deep learning by promoting student engagement. And these can help students develop skills that are essential in the workplace and that transfer to a wide range of settings, things as communication, problem solving, critical thinking. But high impact learning happens when students are actively engaged in their educational process, when their learning goes beyond the classroom to be applied in their personal lives and work lives. Some of the things you may have experienced at Randolph College in terms of high impact experiences are the first year class, our Life More Abundant course, writing intensive courses, service learning courses at Faculty of Design, community-based learning, internships, and also undergraduate research. So one of the things that's really important as well and being recognized more and more is that mentoring is seen as a high impact strategy for promoting student success. So today I wanted to thank all the faculty and staff at Randolph, the mentors that have worked with our students to design and carry out their research projects, their scholarship, their capstone projects, those who've helped them access their RISE grants, traveled with our students, designed service learning opportunities, faculty and staff who've taken students to conferences. All of these things have contributed to your learning and your learning outcomes. So we're thankful for that, and we want to highlight that today. The Center for Student Research supports many of the programs that offer high impact experiences for our students. So we want to highlight our faculty and their scholarship. So when our faculty stay involved in research and professional development and performances, it creates opportunities for our students. So today, Dr. Michael Penn is here to share his work and his scholarship. He's an associate professor in the Department of Mathematics and Computer Science. He conducts research in the field, I have to read this part, in the field of representation theory as it's applied to theoretical physics. His research has been published in the Journal of Algebra, the Journal of Pure and Applied Algebra, the Journal of Mathematical Physics. But last but not least, he's a YouTube math star. He's our YouTube math star. And he's been involved in the popularization of math via 2 YouTube channels with over 220,000 subscribers from over 100 different countries, with a total of 36 million views, averaging 1.5 million views per month. Thank you, viewers. This is being live streamed.
Yeah, I think there's about 100 people in the chat right now.
All right. Awesome. Welcome to Randolph College. Happy to have you. I wasn't really ready to be streamed live. We are excited to have you here today to highlight his work and scholarship and his journey in math. So, thank you.
Well, thanks, Holly, and thanks for everyone coming out. I don't think math people are usually trusted with general audience talks, so we'll kind of see how far I crash and burn. This is exactly the second general audience talk I gave. I gave like a TEDx talk at an online thing in India, but they never put it on their YouTube channel, so I think that maybe they didn't think it was very good. So maybe this one is a little bit better. There is exactly 3/4 of a slide from a research talk that I gave a couple of years ago on this talk. So I guess there will be a tiny bit of the scholarship that I do, but really we're just going to talk about what pure math is in general and why we should all care about pure math, even if it seems like there's no immediate application. So we've got a little bit of a plan. So I'm going to give a little history of myself, like how I came to studying math and kind of what, led me to like it so much. Then we're going to talk a little bit about what pure math is, why it's important, and then we're going to look a little bit about the mathematics community that I've been building online, which is like on YouTube, and I also have a Discord server with a couple hundred members. So anyway, let's get into it. So what's my origin story? So I grew up single mother in Little Rock, Arkansas. So when I was around 6 years old, she went back to college. She had dropped out of college during the normal age, so she went back to college to become an elementary school teacher so that she could have a good, flexible schedule to raise me. And she was afraid of math, as you know, a lot of people are. I think mathematicians are also a little bit afraid of math. You know, all of us reach the point in our mathematics journey where it gets very, very difficult and very, very scary. I think probably professional mathematicians like cry more about math problems than the average person. So anyway, when I was like a plucky 5th or 6th grader, I asked her to teach me algebra, but she didn't. But that was maybe the first inkling that I was going to be interested in math. I went to high school at a kind of world famous Little Rock Central High School. It's well known for the integration crisis in the 50s. So there was always like this, feeling of diversity, and as well as like working past kind of historical wrongs like in my educational background. So I'm really proud of the high school that I went to, maybe more than most, because it holds this really important place in history. Let's see, what do we have next? Okay, after college, I attempted to go to grad school at Indiana University. I say that because as is fairly common, I went to a small-ish state school that didn't have a PhD program and didn't have a big history of sending people to PhD programs in math. And so the first time through grad school was pretty difficult for me because of that preparation. So that's actually one of my huge goals, is to like give that sort of good preparation to all students and make it like universally available. But while I was in Indiana, I was trained on the diving team. I was like an elite diver. I got 4th place in nationals at one event once. A bunch of my teammates went to the Olympics and stuff. And so anyway, this is to lighten the mood, one of my worst dives that I've ever done. So I wish I could say that I had a better one to show you, but I think that would like not provide the lightness of the mood that we're going for here. Okay, so now let's move on to maybe what people think mathematicians do. Maybe these next 2 slides are kind of modeled after a similar talk that I had my friend Chris Sadowski from Ursinus College give in this online seminar that I do. He gave a talk that's similar to this to his college. So I think a lot of people think mathematicians do one thing, but we really do another. So I think maybe some people would say that we crunch very large numbers and solve big equations. But generally, when you're doing math, like the number 5 or 6 is pretty big, right? You're not going to actually have that many big numbers floating around. There's like lots of logic and lots of symbols. And yeah, maybe we will solve some big equations. In fact, like I've done some work where I had to solve big equations to set up some sort of proof. But that being said, I had a computer do it because I'm notoriously bad at like making mistakes on the fly. So maybe the next thing is to write code and algorithms. And for me, that's not the case. I do code a little bit for the research that I do. I write some stuff in Mathematica. There's like a huge need in my area to update that to a new place, but I haven't like jumped into that just yet. And then some people think that we just stare at a chalkboard and make insights. Well, maybe we like stare at a chalkboard and think of the dread of how hard math is. There's a lot of that going on. Okay, so what do we actually do? So we actually take current ideas and abstract them, and then look for connections and patterns between different places in math. So it might be something as simple as abstracting the notion of symmetry, which we'll see later in the talk, or abstracting the notion of like addition and multiplication to mathematical objects called groups and rings or fields or something like that. So we really want to find kind of the most universal underpinnings of the basic ideas that you've seen, for your whole life. And then we want to show new results, follow from existing results with logic. And, to be honest, This is what most, probably 95% of mathematicians do when they write papers. I mean, it's probably most of what academics do when they write papers. Only the hallowed few, the top 5% who have institute positions, are pushing the field forward in that way that you would think about in the movies. Most of us are just like laying bricks, right? And then every once in a while, someone will put a cornerstone in, and that cornerstone will like win them a Fields Medal or a Nobel Prize. So there's like kind of a lot of hard work to get results that maybe not a ton of people are interested in, but if you look at it at the conglomerate, it's all really important. It all works towards an important goal. And then the last one is stare at a chalkboard and make insights. So maybe we do that. I don't know. Like I've got a collaborator friend coming on Sunday that's going to stay for a week, and I think we'll probably be staring at a chalkboard. I don't know if we'll be making insights, but we'll be staring at a chalkboard, so that's cool. Okay, so now what do I do? So like I said, I'm a pure mathematician. I study the field of vertex operator algebras. You know, kind of incorrectly, these are algebraic structures that were axiomatized to study things that string theorists saw in the 80s. I say that's incorrectly because I had this guy, Richard Borchards, who won the Fields Medal for inventing or discovering vertex algebras, give a talk on my channel, and he dispelled that myth. But that's, even though he dispelled that myth and he's the one that discovered the object, that's still sort of like what most people think about is this connection to string theory. And that's because it's like super popular or whatever. It's like real clickbaity, if you will. And then we'll talk about, you know, why should we care about pure math? So I will be honest, the motivation for caring about pure math that I'm going to give you guys, I don't really believe that. It's the one that in a mixed audience is sort of the one that you have to say, right? So I'm going to say something like, oh, there'll be applications coming down the line. It's awesome, right? You never know when the applications are coming. But I think most pure mathematicians would think about math closer to art. It's like art built on a logical framework, right? So what is the purpose of art? What is the purpose of poetry, right? I mean, these things like make us understand what we are as humans, and I think pure mathematics does that too. And I think, you know, maybe at the moment, there's like some sort of barrier for the general population to understand the contributions of pure mathematics in this really beautiful way, but I think that maybe we can break that down, and I think that would like make the world a better place for what it's worth. Okay. So I am going to talk a little bit about math. We're going to see some equations and stuff. So sorry, not sorry, but it'll be okay. Okay, so I study like patterns and symmetries. So like I study algebra, and algebra was born out of like studying patterns and symmetries. So like, yeah, I've got some nice symmetric pictures here. We can see the symmetry all over the place right here. You can have reflections and rotations of both of these pictures, and that provides symmetry. Well, there's symmetries in complicated places in math too. You know, I'm going to show you lots of nice things. Mathematicians today are not like looking at the symmetries of a square. That's already taken care of. But it's a nice picture. So maybe the first type of symmetry we would talk about is bilateral symmetry. So, you know, we are bilaterally symmetrical. In fact, I taught a first-year experience class at a previous institution. No. I taught some class, I don't remember what it was, and the student did a talk at the end about bilateral symmetry, and she showed a picture of a model as is, and then a model where it was just half of her face folded over, so it was actually perfectly symmetric, and it was very unnerving. So it's in fact, yeah, like on the whole, there is bilateral symmetry, but I think what creates a lot of beauty in nature is like slight symmetry breakings, but that's kind of like neither here nor there. But that's what physicists look at a lot. They look for symmetry breakings in their like systems, but again, that's neither here nor there. So one axis of symmetry is common with animals. So there's a puppy. It's symmetric, it's nice, we're making everyone happy. Oh, there's a cute penguin. It's symmetric, it looks nice. And so now we want to abstract the notion of symmetry. So instead of just looking at symmetry as maybe some sort of sameness of one side or the other for a picture, we want to think about it like an action. So what could we do to an object and leave it unchanged? And so in these cases back here that we talked about, we could fold it across that axis. That's the action that we could do to leave this unchanged. And so notice this object, this puppy right here, or this penguin right here, has two things you can do to it to make it unchanged. You can leave it alone, or you could fold it in half and it looks the same, right? And so we want to think about that action as coming from the symmetry. And so we've got a picture of this. So if we apply the fold twice, we get back where we started, right? So we've got two things that happen, and if you apply the folding and then folding again, you get back to where we started. So that forms something called a group for what it's worth. It's a group of order 2. And so now that we've abstracted that notion of folding, we can apply this folding to things that are symmetric and things that aren't symmetric. So the dancing person on the left is not symmetric in the current pose or whatever, but this like bull on the right is symmetric. And so if we apply a folding, right, the bull stays the same, whereas the dancing person doesn't stay the same. So some objects are invariant under the folding and some are not invariant under the folding. And actually, I went in when I made this, and I actually folded the cow because I wanted to, even though you can't tell. I could have just left it as is, but I folded it, and it stays the same. Okay, so here's bilateral symmetry in fancy places. So here's the one serious slide or whatever. So like I gave a talk there's this like big conference every 2 years for the subject that I work in Dubrovnik, Croatia. It's like where they filmed Game of Thrones. It was awesome. It was like a really cool old walled city. So anyway, I gave a talk there with this guy, which was a result with this guy, Dražen Adamovic. He's like at Zagreb University, and then this Anton Milas from Albany. And we showed that this fancy algebra on the left, we won't talk about, and this fancy algebra on the right with this Z2 up there are the same. So what does that mean? Well, it would take like a month to build up all of the details to say what that's the same. But this Z2 right here essentially means that we've folded this space on its own. So we've applied a bilateral symmetry to this fancy space right here, the n equals 3 conformal superalgebra. Physics, I think people know that stuff. And we got this other algebra over here. So there's bilateral symmetry in really, really, really fancy places. Oh, and just like here's one thing about math. If you're ever like, I mean, there are faculty here, if you're ever on like a committee where you're like judging how a mathematician did or whatever, authors are always alphabetical. We don't believe in hierarchy in pure math papers. They're always alphabetical. And when people give talks, they give the full name of the other people and just the like initial of yourself, or sometimes just an underscore. So there's this kind of weird stepping away from your work in mathematics, which I think is really nice. But again, that's kind of not super related to the talk. But anyway, the point of this slide is that there's this bilateral symmetry in really fancy places. Okay, well, there's other types of symmetry as well. There's rotational symmetry, right? So for example, we could take this triangle and apply a 0-degree rotation and it stays the same. I've labeled the vertices A, B, and C, but you don't want to think about those as part of the triangle. That's just up there for like place holding or whatever. Then we could apply a 120-degree rotation, and notice vertex A moves from here to here, B from here to here, and C from here to here. But the picture is the same, right? So there's this 120-degree rotational symmetry of the triangle. There's also a 240-degree rotational symmetry of the triangle too. That would be like applying the rotation twice. So this would be an example of something with rotational symmetry. Equilateral triangle. Oh, I said equilateral triangle in a video once instead of equilateral triangle, and people like slammed me, so we'll see how that goes. But you could imagine this is, instead of being an equilateral triangle, this is a regular 3-gon, right? So it's like a polygon with 3 sides, all the sides are the same. And so the 360 degree rotation gets us back to where we started. So that's important, getting back to where we started. There are only a finite number of rotations that we can do that leave us in the same place. And if we apply one after another, after another, after another, we'll eventually get back where we started. It's like a closed loop. So obviously you can think about lots of pictures with more symmetry than the triangle. So a square has this 90 degree rotational symmetry. You can obviously rotate a square 90 degrees. This hexagon has a 60 degree rotational symmetry, and then this octagon has a 45 degree rotational symmetry. And you can imagine if you rotate a square 4 times by 90 degrees, you get back to the same place. If you rotate a hexagon 6 times in the same way, you get back to the same place, and an octagon 8 times 45 degrees, you get back to the same place, because all of those add up to 360. Okay, so we really want to like work towards an application. So I need one definition to do that, and that is to look for this rotational symmetry in numbers. And so right now we just looked at nice pictures, but we do need to look at numbers for a little bit. But you know, I think it'll be okay. So here's a definition that we need. So we know it's like a real math talk if we have a definition. So we've got a definition. This is the only definition. We'll do some examples so we know what's going on. So we say that A is congruent to B mod n. So that's how we read that. A congruent to B mod n. If A and B have the same remainder when divided by n. So that means you just divide them both by n and keep the remainder. That's all you care about is the remainder. So that means there's only n minus 1 remainders, because you wouldn't take a remainder larger than the thing that you're dividing by. So let's look at a couple of examples so we know what's going on before we put this back into terms of rotational symmetry. So 7 is congruent to 2 mod 5. That's because if you divide 7 by 5, you get a quotient of 1 and a remainder of 2. So 7 and 2 are the same modulo 5. It's like having a clock with 5 hours, right? I mean, we have a clock with 12 hours, but you know, if you look at 14 hours from now, that's the same thing as adding 2 hours, right? So 14 hours from now is something like 1 o'clock in the morning, probably. So this is just a clock with 5 hours, so that's okay. And then 13 is congruent to 4 mod 9 for the same reason. So nothing fancy is going on here. This is like the quotient with remainder type stuff that my kid who's in 5th grade did a couple of years ago or something, right? So you divide 13 by 9, you get a quotient of 1 again and a remainder of 4. So 13 and 4 are the same mod 9. So 13 o'clock and 4 o'clock would be the same if we had a 9-hour time system, right? Okay, and then finally, like that hard one. So 59 is the same thing as 3 mod 7. That's because if you divide 59 by 7, you get 8. 8 times 7 is 56. I was not very good at my multiplication facts until I had a kid that I taught them to, so it's not like a requirement to be a mathematician to be good at arithmetic. I just remembered them all after the fact. So 56, but then that gives us a remainder of 3. So we have 8 remainder 3. So after keeping the remainder, we just have 3. So what's nice about this is there are only so many numbers that you need to look at if you're working mod 5, 9, or 7. You only need to look at the numbers 0 through 4 in the case of 9, 0 through 8. So 0 through 4 in the case of 5, 0 through 8 in the case of 9, and 0 through 6 in the case of 7, because you wouldn't keep a remainder larger than that. Just like, unless you're talking 24-hour time, you wouldn't say 13 o'clock, right? You would say 1 o'clock p.m. or something, right? Yeah, okay. So now we want to put these two ideas together, this idea of modular arithmetic, that's the fancy word that's going on over here, modular arithmetic, and then this thing of symmetry in a n-gon, in this case a 4-gon. So I think you call that a square if I'm not incorrect, yeah. So what's cool about this is that multiplying by 2 and then reducing mod 5. When I say reducing mod 5, I divide by 5 and keep the remainder. That's in fact the same thing as doing a 90-degree rotation. So it exhibits the same sort of rotational symmetry. And we can see this by the following chart, which we can work through. So I think we can all agree that 2 times 1 is 2, right? So if we multiply 2 to 1, that moves this vertex over here, right? Because 2 times 1 is 2. Then 2 times 2 is 4, so nothing fancy's happened yet. But I think we can all agree with that as well. Multiply this vertex by 2, we get to 4. Okay, now here's where it gets like fancier. So 2 times 4, so what's 2 times 4? 8. But 8 mod 5 is 3, because if you divide 8 by 5, you get a remainder of 3, right? It's a quotient of 1 and a remainder of 3. So that means when you multiply 4 by 2, you get over here to 3. So that's cool. We've rotated all 3 of these vertices in the right kind of orientation to exhibit a 90-degree rotation. We just want to make sure the last one works. So if we do 2 times 3, what's 2 times 3? 6. What's 6 mod 5? 1, because you like divide by 5 and keep the remainder. The remainder is 1. So what I'm getting at here is like there's this beautiful like relationship between the rotation, which is happening geometrically, and this modular multiplication, if you want to use like a fancy word, this multiplication by 2 and taking the congruence mod 5. Now there's a lot of fancy stuff going on here, which I think probably Mark would know about. Not probably, he would know about. And then everyone else like in here that was in my number theory class would know about, and then people in the chat would maybe know about as well. Like I chose 2 carefully. It's something called a primitive root. It's important that we're working mod a prime. All that kind of stuff is important. So I'll just say all of those things so that I sound smart. Okay, so let's like review what happened. If we multiply by 2, it's like rotating by 90 degrees. So we just noticed that. If we multiply by 4, it's like rotating by 180 degrees, because it's like 90 degrees twice. If we multiply by, if we multiply by 3, it's like rotating by 270 degrees. Remember, 3 was the same thing as 8, and 8 is the same thing as 2 cubed. So 3 90-degree rotations is a 270-degree rotation. And then finally, a full rotation happens if we multiply by 1, or by 1, I guess. So here's just like a chart of what went on. So multiplying by 2 is rotation by 90 degrees. Multiplying by 2 squared is the same as rotation by 180. 2 cubed, 270. 2 to the 4th is 360. Now we're going to get like real crazy math person here and look at the patterns. So rotating a square by 360 degrees is like doing nothing to it, right? Well, rotating any object by 360 degrees is like doing nothing to it. Here, we took 2 to the 4th power. We've got a square, we're working mod 5, square 4, 5. Oh, 4 is 5 minus 1, right? So these are the patterns we kind of look for. And so we look for patterns like this in pure math, and then we try to prove them carefully, right? So it looks like 2 to the 5 minus 1 is like doing nothing at all, rotating 360 degrees. And it turns out that there's a result for this in general, and it's called Fermat's little theorem. And it says this, so this is like the fancy math result, super famous. So it says if P is a prime, so 5 was a prime, and A is not a multiple of P, then A to the P minus 1 is congruent to 1 mod P. So in other words, if you build some sort of n-gon, P minus 1 gon, out of this prime P, and like your action is multiplying by A, if you do it P minus 1 times, it's like doing nothing. So that's how we want to think about this. This is that thing that we saw on the last slide, but just abstracted. Instead of multiplying by 2 and rotating a square, we're multiplying just by some other number, and we're rotating a larger polygon. So the little picture of it's kind of like this. So here we've got all of the numbers, 1, 2, 3, 4, blah, 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 blah. So multiplying by A to the P minus 1 is like rotating this polygon all the way around. That's how you want to think about this. So there's symmetry in this multiplication if you're working, in this modular arithmetic. Okay, so good. That's the hardest math done. So that's good, right? So maybe now we're going to talk about why we should care about this result, why we should care about pure math in general, the reason that I don't really believe in, like I warned you. So Fermat's little theorem was discovered in 1679. So it was one of these things that was left by Fermat, not proven by Fermat. Oh, I had the date in my head of when it was first proven by someone else, but I forgot it at the moment, so I apologize. It was not applied to anything at all until 1977, and it was applied to cryptography. So that's almost 300 years from the discovery of this result to the application of the result. And you might say, well, okay, well, what's the application? What application could we have for Fermat's little theorem? Well, it turns out that it's like the most important application for the modern world, and that's called public key encryption, in particular RSA. And so what this allows is for encrypted data to be safely sent over the internet. So the mathematics that makes this encryption so secure is built off of Fermat's little theorem and its slight generalization, which is called Euler's generalization to Fermat's little theorem. So without this result, we would not be able to do like any online banking. We wouldn't be able to buy stuff on Amazon. We wouldn't be able to, like, Randolph wouldn't be able to like take tuition payments online. Anything like that would be impossible. And so that's a big deal. RSA is responsible for our ability to securely share information on the internet. And without number theory that was discovered 300 years ago, it would be impossible. It took 300 years from its discovery to its application. You know, lots of people were interested in number theory, but it wasn't until these 2 computer scientists and 1 mathematician found this algorithm that there was an application. It's not totally true. It was found by a mathematician who worked for intelligence agency in Britain, in 1973, but it wasn't declassified in time, so it's still named after these 3 guys. So, still 1973 to 1679. That's still a long time, right? That's like almost as. I mean, I'm not very good at arithmetic, but that's like I think that's almost the same amount of time. Okay, so here's some other examples of math that maybe went for a long time without application. Not quite as long, like Fermat's little theorem is the shining result. All of these applications are called like the golden goose. That's like the word for it. So pure math that doesn't seem like it's going to have an application then has an important application. So Fourier series, so this guy Fourier wanted to take periodic functions. Those are functions that repeat. Or they're periodic. And he wanted to write them in terms of sines and cosines, which is something you might have learned if you took a trigonometry class. And it was applied to telecommunications, so it helps like cell phone networks work. So I don't think there were cell phones in 1807, so he wasn't thinking about those applications. There are other applications to Fourier series, but that's one of them. Okay, so logic. So in the early part of the 20th century, was when mathematicians started to prove things very, very carefully. Before that, it was like kind of sketchy. But starting in the beginning of the 19th century, kind of built off of this math cult, Bourbaki, they wanted to put really, really firm logical footing in mathematics. And among other things, crazy things happened there, like there were results that were proven to be unprovable and all of this like crazy stuff that could fill up an entire other talk. But Turing was part of this, and he said, hey, I want to make a machine that could decide if a logical statement is true or not. That's all he wanted. Is the logical statement true or not? But it turned into the computer, which is probably pretty important for our day-to-day lives, right? So another instance of this like thing that was devised for purely intellectual gain is really important. Okay, now topology, this is a newer one. So topology is like studying broadly the shape of things, right? So it was developed in the early 1900s by several people, including some of the people from Bourbaki. And it's important really recently to modern data science. There's this thing called topological data analysis. Like a lot of people who work in topology nowadays hopped on topological data analysis so they could get jobs. Just like a lot of people in number theory hopped into cryptography so they could get jobs. So essentially what's going on here is like, there's this big study of data, right? Like all these websites are taking data or whatever, but that builds like these very, very large multi-dimensional arrays of data. And so the topological data analysis is studying the large geometric structure of that data. I have a former student that did like a pure math like senior project with me, and now he's studying like the geometry of data in grad school. I think he's gonna graduate in a couple of years. So, I mean, there is like, this is very, very important and very, very real right now. And then there's this other branch called category theory, which is like perhaps the most abstract branch of math. So if I were smarter, I would do category theory, because I'm like just obsessed with like super abstract math, but I'm not like very good at it. For what it's worth. And it aims to unify mathematics. Like people have like thought so hard about abstract category theory and stuff that they've like gone a little bit crazy. So, but it's really important to modern programming languages. In fact, category theory can be used to test a computer program that you don't have a chance to test. So for instance, like you're gonna send a satellite, right? You're gonna send a satellite to the Jupiter or something, right? There's a lot of code on that satellite. You can't send the satellite to Jupiter as a test, right? I mean, it costs like billions of dollars. But you can run some, I don't exactly know how this is done, but you can run some sort of test on the code using categorical techniques to make sure that you're probably in a good place. Okay, so now, maybe are we all convinced that math is important? Okay, cool. I've got everyone in the room. Okay, so now, I mean, I guess maybe we need to talk about this like weird thing that I do also. So what am I doing to promote math? Well, actually just before the pandemic, I started this YouTube channel because I was super psyched to flip my classes. You know, like students watch videos and then they come in and they just do problems on the board and I heckle them the whole time. It's awesome. It's like my favorite thing to do in the world. And I think it's good for learning, right? My students? Okay, I've got some thumbs up. So anyway, so I just put them on YouTube. And then, I don't know, I just like made it this sort of game to see if I could get them noticed by people other than my students. So, I mean, I eventually did, and now it's like quite big. And I have this YouTube channel, this main channel that has 217,000 subscribers. And I think if you go to the analytics for the Randolph College website, a lot of clicks come from this. Like a very decent proportion of the clicks come from this thing right here. So I think that's cool, and I'd like to do more if anyone there is like in here. Like I'd like to do more to help. So like I'll do an ad read for Randolph College. Like 25,000 people will do it. We'll see it, I promise. Okay, so the reach of new media is just outstandingly remarkable. At least the reach that I've built somehow is very remarkable. So this is the last 90 days. So 87.2 million impressions. 4.4 million total views in the last 90 days, 1.4 million unique viewers in the last 90 days. So I think that's a pretty big reach. Like that's a pretty big audience that can be like pushed toward good. You know, the good of pure mathematics or the good of whatever, right? And so now I'll talk about some stunts that I've done for a reason. So last summer, I thought it would be a good idea to teach an entire Calculus 2 class without stopping. So I did. It took 12 hours. I skipped some stuff. I apologize. I think we had like 300 or 400 people average in the stream at a time, 800 people peak in the stream. At the end of the stream, we had like 25,000 unique people in and out. Now the video is like 60,000 views, so it has a pretty big reach. I don't know how good this is for learning Calculus 2. I think I did an okay job, but I mean, I was on the fringe at the end. Here, we can watch the. Okay.
Got to do it tonight. We're back up though. Hopefully we can get people like to know that it's happening. Okay. So
this is what it was for 12 hours. People were there, I don't know.
Plus the third one, that's going to be a half choose 2, so that's going to be a half.
This is really interesting because I do like 4 arithmetic mistakes in the span of 10 seconds. We'll point them out.
16.
So there's
our approximation.
a half times a fourth. Watch this.
This is 2, and then 1 plus, that's going to be 3/8.
That's not true.
16 times 2 is 32, 64, 128, minus 120.
I left off the 1.
Yeah. Are there any problems we want to do from chapter 6?
So that was me 12 hours in. So I think it was okay, right, for 12 hours in. So I don't know, like, obviously it's different or whatever, but like, teaching take 2 is it's not quite as fast as this. Yeah. Okay, so I'm also like really into rock climbing. So I've done 2 rock climbing math challenges. So this first one is this like climbing test that was going around rock climbing YouTube for a while. So it was this guy Magnus Midtbo, who is a Norwegian climber. He started this test or whatever. So I made a video where I did the climbing test, and then I also did 2 problems from the Norwegian Math Olympiad. So like I do a problem from the Norwegian Math Olympiad, and then I show myself doing the test. And then I also did this thing last summer where I did the Gaussian integral. It's a math problem, while climbing a 513 rock climb. And so I think I've got a little clip of that we can watch. Sorry, this is loud. So as you can see, I have a whiteboard hanging from my back. It's not a chalkboard, so it's not like as pure as I would like it to be, but I got some like kids that were living on the road to help me film.
So today we've got a really classic integral known as the Gaussian integral. We're going to calculate it using arithmetic. So let's start by squaring it, and then also taking the square root. So that means we haven't done anything. Now, if we do that, get the square root of the integral from minus infinity to infinity, e to the minus x squared dx times the integral from minus infinity to infinity, e to the minus y squared dy.
My abs were sore for like 5 days afterwards.
Now we can change.
And then I climbed to the top. Gratuitous victory whip. Okay, so I'm like really looking forward to trying to do some more challenges like that, but you know, I haven't really gotten around to it yet. So I did some another interesting video recently. I taught my niece some math. So I do this weird non-math podcast with my niece and nephew, because I don't know, I'm a crazy person. And she's a student at Queen's University Belfast. She's like, that's her actual school. So whenever I meet a student here that's thinking about going, I'm like, it's awesome there. My niece goes there. You should go hang out with Grace. She's great. She's studying philosophy and politics. So I taught her, she didn't really know much math. I taught her how to find the last digit of this number, which seems crazy, but there's a trick. I mean, there's always a trick, right? So it's 7. Spoiler alert, it's 7. And it doesn't take that long once you know the trick. So we don't have a clip for this, but that was fun too. I'm really interested in like doing things where I teach math to non-math people. I think that's sort of fun. Okay, wait. So next, maybe I'd like to do more challenges. So math professor learns how to do something. Any of you guys in the audience, if you guys want to teach me something, we'll video the process and make a short film about it. I'm down. Math professor tries something. I don't know. I don't think there are any coaches here. If there are any coaches here, I'll do a workout with one of the teams. We can film it, and that'd be super fun, right? Anyway, so I'm pretty much down for anything, and I hope we had fun.
Thank you so much. Thanks, everybody. There are more events this afternoon.
Wait, do we have questions?
Do you want to answer a question?
I told the chat I would take questions. So, I mean, I'll take questions from you guys too. Yes?
I have a question, it's not math related.
Yeah.
It's a YouTube related.
Okay.
What's your crew? How many people do you have on your crew to produce those?
Okay, so like, so that's like kind of interesting. For a long time, it was just me. I have a setup in my basement. That chalkboard's in my basement. I have studio lights and stuff, and then like a pretty fancy camera, a cinema camera. And it was just me, and I did all the editing. But then I like started paying someone to edit, Noah Carney. He's really fast. And then I have these other two students that are working for me too right now. Yeah. So, but I don't know, a couple. Yeah.
Thanks.
All right, so we have a question from the chat. Would you ever consider getting into the philosophy of mathematics?
I don't know. I mean, I like the idea of that, but I mean, there's only just so much stuff you can do, right? Yeah, I'm sort of maxed out. Yeah. I don't know anything about the philosophy of math. Maybe numbers aren't real. I know that that's a question. This is true, right?
Yeah.
Yeah, maybe numbers aren't real.
I can't say anything else.
Yeah, I don't know.
Just know it's a question.
I don't know, maybe they're not real. Anything else?
If you dropped the whiteboard when you were rock climbing, did you have a plan for that?
No, I didn't, but I did have it fairly secure. Like I had it secured a couple of different ways, so it was slung over me, and then I think I also had it clipped in to my harness. So it was okay. I was a little bit worried of when I took the victory whip that it would like go crazy in the air and stuff, but I was fine. Yeah.
Earlier in the talk, you talked about pure mathematics being like art, and you said that it reveals stuff about being human. Can you say a little bit more about that?
Yeah. Yeah, good question of this thing that I just said offhand. I don't know. I just think like mathematical results are, like pure math results are kind of akin to other types of big things that humanity has created. Maybe something like that. So like, I don't know, the Mona Lisa, right? That was nice, right? Well, I think like the Pythagorean theorem was also nice, right? Fermat's theorem, even if it hadn't been applied, was also nice, right? I think maybe it's kind of more in line with that. Like I think maybe mathematicians are shown what it's like to struggle, like being human is to struggle, showed how to struggle like in the process of them doing their mathematics for sure. Yeah.
That's funny that Kaya suggested that question because that was along the lines of my question, which for a long time ago I dabbled briefly in the perception of attractiveness. And what you said about bilateral symmetry really resonated because what we find when we ask people to rate attractive faces is we say we really like symmetry, but if something's too symmetric, we don't like it. So we like symmetry up until a point, at which point we want to break it a little bit, and that's the most attractive. And so to me, I just, like, have you ever heard anything about like that in terms of perception of attractive faces?
No. I just know that like when I saw the perfectly symmetric face, it was creepy.
It is.
Yeah. And I know like pieces of art have slight changes in symmetry that make them more more beautiful. Yeah, but I don't know any details of that.
Yeah, so I know you have some students who also are very involved in music, and there's a bunch of STEM students who are involved in music. So would you ever think of doing like a video or like a talk about like the math of music?
Yeah, I would have to learn about that.
Yeah.
But yeah, sure. I think there's something Fourier series in that, right?
I think so, yeah.
Yeah.
All right, so we have a few people that are asking if you could walk us through a day in your life. Like, what do you do on your average day? We want to like know how you do it all.
I've done that before. There's like a 50K Q&A where I talk about that. Yeah. All right, are we good? Yeah.
Can we do a backflip?
Yeah, we can do that. I think we can call it maybe.
Take more of his classes.